today we shall discuss about evidences for the quantized energy levels, that is atomic spectra. Before going into atomic spectra, let us have a look into some properties of light. Children, as you know, light is a form of photons of energy only. Correct? That is, when light falls into a particular medium, you have studied the experiment of light passing through a glass slab. Suppose this is a glass is another medium and air is another medium. Now, if as you have seen, when light falls, this is a ray of light. And if you allow this light to pass through this, it is expected to go in straight line, isn't it? But what you will observe is it gets bent in its path. Correct? The bending of light, this phenomenon you studied as a refraction of light. Correct? In which if there are a bunch of light in which we have studied that the deviation of light from its original path depends upon the wavelength of light. As you know, white light composed of 7 colors. These 7 colors are actually 7 different wavelengths only. As you know, if a white light allowed to pass into a prism, dispersion takes place. That is, the path of light, you can observe different varieties of colors are coming out. Here you will observe violet, indigo, blue, green, yellow, orange, red, in which violet will have the maximum deviation because violet has a shorter wavelength. And red will have least deviation because red is having the highest wavelength. The light with the highest wavelength will get a small deviation or a little bit bending only will take place, but the light with the shorter wavelength. But of course you must remember the shorter wavelengths have the highest frequency. Okay, so the shorter wavelength will have highest frequency and the longer wavelength have the shorter frequencies. Okay, now let's look into the here what you observe here is the light, this colors will be merged into the another one. Means you cannot exactly separate out this vigor. Vigor is composed of 7 different colors which are actually merged one to the other one. Okay, so this merged spectrum which is produced, that we call it as a continuous spectrum. Why it is called a continuous spectrum? Because this spectrum is actually one color will be merged with another color, because where violet, indigo, blue, green, orange, red, in which one will be merging exactly, you cannot distinguish one from the other one. That's why they are called a continuous spectrum. Okay. So students, here you can see that white light falls into a prism. It splits into 7 different colors you can see here. Correct? This phenomenon is called dispersion of light, that you can also see in the rainbow. The spectrum of white light that we can see ranges from violet, indigo, blue, green, yellow, orange, red. And here you can see one merges with the other one. Correct? So because of the, you cannot distinguish the particular wavelength of light from one another. Because of that reason, this particular type of spectrums are also called continuous spectrum. Children, now listen here. If you take a particular cylinder or a container in which gas molecules are present in it, we are taking a hydrogen gas, okay, and if we heat this one, we have to heat it, then these rays produced are allowed to pass through the prism, and they will produce light of having a particular frequencies. You cannot find here a continuous spectrum. Here certain colors will be missing out here, or certain particular frequencies are actually not seen. Here you can observe that substance is heated and the emitted light is allowed to pass through the prism. Emitted radiations or the diffracted light will consist of certain particular colors only. Those lines we call it as line spectrum or line emission spectrum. The emission spectrum of atoms in gas phase do not show continuous spread of wavelength from red to violet. Rather, they emit only at specific wavelengths with the dark spaces between them. Such spectra are called line spectra, or we can also call it as atomic spectra, because the emitted radiation is identified by the appearance of bright lines in the spectra. Another one we have is if you allow white light to, this is our white light, to pass through a particular sample. Okay, after passing through this sample, if that emerging light is allowed to pass through a prism, emerging light is allowed to pass through a prism, they will also produce a particular kind of spectrum which consists of which also will be lacking some particular lines in the, or some particular wavelengths are missing. Those wavelengths which are missing actually due to the absorption of the sample which is present in it. Okay, the molecules or the sample absorbed certain frequencies. Because of that, the rest of the frequencies or the wavelengths are only emerged out as the colors. This type of spectra is called absorption spectra. Absorption spectrum. White light is passed through the vapors of a substance, and transmitted light is then allowed to strike a prism. Dark lines appear in the otherwise continuous spectrum. This is known as absorption spectrum. The dark lines indicate that radiations corresponding to them were absorbed by the substance from the white light. That is, that particular substance which we kept in between, it absorbed certain wavelength of light. That energy of light is being absorbed. It may be noted that dark lines appear exactly at the same position where the lines in the emission spectrum appear. So children, what is the main difference between line spectra and absorption spectra is, absorption spectra, one sample through which white light we are passing, and certain particular wavelengths are absorbed by the sample, and the emerging light will produce a particular spectra that we call it as absorption spectra. And in line spectra are produced when a particular gas is heated. The excited particles are actually passed through the prism, and the lines or spectra of colors, these colors will contain a particular wavelength in which dark bands are seen. What is the main important thing we have to listen from here is this line spectra has got very much importance because a particular element will have a particular type of line spectra only. Okay, so we can identify which type of element is present in a particular sample by looking at their line spectra. If we are able to identify their line spectra, through which we can find out the which type of element is present in it. It is like the fingerprints of human beings. A particular human being will have a only unique fingerprint, isn't it? So the same like that, a particular element will have a particular line spectrum. Okay, it will not be changed. So by looking at the line spectrum, the element can be easily identified. So students, the atomic spectra is produced by the interaction of light with matter. The study of emission and absorption spectra is referred to as spectroscopy. So children, what is spectroscopy? The study of emission and absorption spectra is referred to as spectroscopy. This is a branch of science which deals study of emission and absorption spectra. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. A continuous radiation is passed through a sample which absorbs radiation of certain wavelengths. Thus, missing wavelengths corresponds to the radiation absorbed by the matter, which leaves dark spaces in the bright continuous spectrum. This is referred as absorption spectra. The spectrum of white light, which ranges from violet at 7.5 into 10 raised to 14 Hz to red at 4 into 10 raised to 14 Hz, is called continuous spectrum. The emission spectra of atoms in the gas phase do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelength with dark spaces between them. Such spectra are called line spectra, or it is also called atomic spectra. Now let's see the line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. Here you can see when an electric discharge is passed through gaseous hydrogen, the hydrogen molecules dissociate and the energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. A scientist named Balmer showed in 1885 on the basis of experimental observations that if spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey a particular formula, that is 1 by lambda. 1 by lambda is wave number, which is equal to a constant into 1 by 2 square minus 1 by n square centimeter inverse. Here n is equal to 3, 4, 5, etc. up to infinity. The series of lines described by this formula are called Balmer series. The Balmer series of lines are the only lines in this hydrogen spectrum which appear in the visible region of electromagnetic spectrum. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the spectrum, that is hydrogen spectrum, could be described by a general formula, that is 1 by lambda is equal to a constant that is similar in a Balmer's formula into 1 by n1 square minus 1 by n2 square centimeter inverse. So this is actually the general formula for any series. Students, the first 5 series of lines that correspond to n1 is equal to 1, 2, 3, 4 and 5 are known as Lyman, Balmer, Pascal, Brackett and Fund series respectively. The spectral lines for atoms of hydrogen were found in different spectral regions. As you know, Balmer discovered these spectral lines in the visible region, whereas Lyman found in the ultraviolet region, and Pascal, Brackett and Fund found the spectral lines in infrared region. Rydberg has given this simple theoretical equation for the calculation of wavelengths or wave numbers of the spectral lines in different series of hydrogen spectrum. This equation is known as Rydberg formula or Rydberg equation. Here, this constant value is also expressed as RH, where RH is called Rydberg constant and its value is 1.09677 into 10 raised to 5 centimeter inverse or 1.09677 into 10 raised to 7 meter inverse. Here this n1, n2 are integers. Always remember children, n2 should be always greater than n1. For any particular series, the value of n1 is constant while that of n2 changes. For example, for Lyman series, n1 is equal to 1, n2 is equal to, it can be 2, 3, 4, 5, etc. For Balmer series, n1 is equal to 2, that already Balmer is derived, n1 is equal to 2, n2 is equal to 3, 4, 5, 6, etc. And for Pascal series, n1 is equal to 3, n2 is equal to 4, 5, 6, 7. And for Brackett series, n1 is equal to 4, n2 is equal to 5, 6, 7, 8. For Fund series, n1 is equal to 5 and n2 is equal to 6, 7, 8, 9, etc. And children, remember, this relation is valid for hydrogen atom only. Of the all elements, hydrogen atom has the simplest line spectrum. Line spectrum becomes more and more complex for heavier atoms. There are, however, certain features which are common to all line spectra. That is, line spectrum of element is unique and there is regularity in the spectrum of each element. The question which arises are, what are the reasons for these similarities? Is it something to do with the electronic structure of atoms? These are the questions need to be answered. We shall find later that the answers to these questions provide key in understanding electronic structure of these elements. So children, Bohr's model of hydrogen atom we will discuss in the next module. Thank you and have a nice day.